This is the presentation for the audio amplifier project by Prayan, Baida, Wincy Wang, and Armando Peña.
As you can see in the diagram, there are two main circuits. One is in the right, one is in the left. The left one is the preamplifier. One of the right is the power amplifier. In order to build the audio amplifier, we first develop the preamplifier and the power amplifier. The input for AC signal is going to be 50 millivolts peak to peak, and 1 kilohertz sine wave. We also using 30 volts DC supply. For the experiment, we first work with the pre-amplifier stage and verify of the output meets the required power meter. After that, we worked on the power amplifier and verified if all the conditions for power amp is satisfied. Once all the required conditions for both stages was achieved, we combined both circuits together.
In order to design the preamplifier, we start assuming a few values for the VAT-Q7. For example, we assume that the voltage in the meter will be 10 volts and the voltage in the collector will be 15 volts. The resistor emitter could be 5K and the resistor for the collector will be 7.5K. Also for this section, the preamplifier will be assuming that the capacitor will be 7.3 microfarads. Now the next step is to find the value of the base voltage and finding the rate of resistors R25 and R26. This was accomplished by using equation number 1, in which a voltage base is equal to 0.7, which is the VBE voltage plus the voltage in the meter, which is 10 volts. So the total voltage for the voltage base is 10.7 volts. Then using equation number 2, the rate of R25 and R26 was found, but by saying that the voltage base is equal to VCC, which is 30 volts, times R26 divided by R25 plus R26. Solving this equation for R25 and R26 gives the rate of 1.807. So the R26 value was assumed to be 5.6 kilo ohms, and then the R25 value was obtained and to be 10k ohm. Now we decide to show the pipe diagram for the VAT-Q7 to have a better understanding of the calculations involved in this project. For this reason, we found R5 to be equal to R25 in parallel with R26. IB was found by using equation 5, but before using equation 5, we had to see the relationship between IB and IE shown in equation number 4. Therefore, going back to equation number 5, we say that VCC, which is 30 volts, equal to RB times the current in the base plus VBE plus the current in the meter times the resistor in the meter. That led to IB equal to 58 microamps. Now, going back to equation 4, we can see the relationship between IC and IB. So, using that equation, we found the value of IC being a 5.8 milliamps. In this diagram, I pipe was found by equation number 6, in which we say that beta times 0.025 divided by IC. Rin in this circuit was found by computing R5 in parallel with R5. Ro in equation number A was found by VA and divided by IZ. The value for VA can oscillate between 10 and 100. In this case, we choose 100 and we obtained 17k ohm for Ro. Also, the value for Rout was found in here as shown in equation number 9, where we use Ro in parallel with Rc. Similar other equations can be seen as equation number 10, and equation number 11 shows how to obtain the gain for the preamplifier, where RL will be the input resistance in the power amplifier. Also, for the preamplifier, we are required to find the drain resistor and also the source resistor. So in this case, we assume that the gain of the JFET J2 oscillate between 5 and 10 volts. So taking the gain of the JFET as 5 volts and using equation 13 and given the value of R24 as a 1K, it was found that RA is equal to 5K kilo ohms. Also, in this preamplifier section, we found the reference resistor, the Rref, which is R32 in the diagram shown in slide 1. And the reference resistor was found using equation 14, in which we say that the voltage gain of the preamplifier oscillates between 20 and 30 volts. So taking the voltage gain at 30 volts, we say that 30 equal to 1 plus R32 divided by R24, and that led to the value of the Rref, which is R32 equal to 29 kilo ohms.
Alright, this is our preamplifier circuit in PSpice. The circuit was designed in PSpice using the calculated components values for resistor and capacitors. The PSpice simulation was performed in order to test whether the circuit meets the required condition for the preamp stage. The objective of the preamp was to produce a gain value between 20 to 30 volt by volt. For PSpice simulation, we performed a time domain and frequency response simulation. The graph on the left shows the results from time domain. Based on the observation of the graph, we can see that the voltage peak-to-peak value is approximately 2.8 volts, which means the gain for the circuit is around 28 volt by volt. This perfectly fits our required condition for preamp. The graph on the right shows the frequency response. We can see that the graph peaks around 300 Hz and plateaus around 1 kHz, and the gain is approximately 27.75 volt by volt, which fits our design value for preamp, since the gain for the preamp was supposed to be between 20 to 30 volts by volt. After the desired PSpice results were achieved, the real circuit was built and tested. The figure on the left shows the oscilloscope captured image of the input signal. The graph on the right is our output signal for the preamp. As you can see, the input signal has 100 millivolts peak to peak, while the output signal has a peak to peak value of 14.50 volts, which means that the signal has a gain of 145 volt by volt. This means that this does not fit our design requirements. However, due to the limited time constraint, we chose to stick with our component values and design the power amp in a way that the components for the high gain of the preamp is compensated using the power amplifier.
For the power amplifier, we assume that R31 was equal to 10K, R41 equal to 1K, R37 and R38 equal to 2.7. And all the capacitors for this section, we assume that they were equal to 3.3 microfarads. Also, since two Darlington were used and they were connected in the power amplifier, we use equation number 14, in which we multiply 4 times the VBE equal to 1 plus R34 divided by R35 times VBE. And by computing this equation, we obtain a rate of 3. So we found that R34 was equal to 3K and R35 was equal to 1K. For the same part in the power amplifier, we compute R39 and R40 using equation number 16, in which VV equal to VCC times R40 divided by R39 plus R40 give we obtain a rate of 1.8. So R39 was found to be 50 kilo ohms and R40 was found to be 10 kilo ohms.
After the completion of the preamp stage, we went on to design the power amp stage. The following diagram shows the PSpice circuit for the preamp, which was designed using the computed component values. Similar to the preamp stage, AC signal with 50 volts peak to peak was applied, and the DC volt was set to 30 volts. The expected gain for the power amplifier is supposed to be between 2 to 8 volts. Similar to the preamp stage, we performed transient and frequency response simulation for the power amp. From our observation, we can see that the graph of the transient simulation is stable and a stable sine wave with less distortion. From the frequency response graph on the right, we can observe that the signal peaks at approximately 1 volts. This means that the maximum gain that can be achieved is 1 volt. Since the input signal is 100 volts peak to peak, the gain for the power amp is around 10 volt by volt, which perfectly fits our design criteria. Once the conditions for the preamp and the power amp stage was satisfied, we put both the circuit together in order to perform tests to verify the desired results, if the desired results was achieved. The goal for the amplifier circuit has to produce an overall gain of 200 to 300 volt by volt. Frequency range has to be within 20 to 20,000 Hz. Like the preamp and the power amp stage, an input signal of AC 50 millivolts peak to peak and a DC signal of 30 volts was applied to the circuit. In PSpice, we performed both frequency response and time domain simulation.
The amplifier circuits we used is a class AB amplifier, since the goal of the circuit was to produce an output that shared similar characteristics as an input signal, but should have an amplifier signal to fit the load requirement. AB amplifiers produce a high efficiency and lens distortion. In this project, we successfully built an audio amplifier powered by a cell phone. We divided this project into a pre-amplifier and a power amplifier. In the pre-amplifier, we obtained a gain of 28 volt per volt, and the pi model diagram Rin was greater than Rout, which has an expected value to be able to maintain a lower loading effect. The gain for the power amp is 10 volt per volt.